Okay, so now that you've learned a little bit about friction, let's see if we can actually apply it to some problems. So here it says a cruise ship passenger uses a shuffleboard cue to push a shuffleboard disc of a mass of 0.4 kilograms. So that's a known right off the bat. Horizontally, so that does mean that we are just immediately dealing everything in the x direction. Along the deck, so the disk leaves the queue with a speed of 8.5 meters per second. So that tells me one thing. It tells me that my V initial is 8.5 meters per second, but it also tells me when I start moving that I have a force of kinetic friction. So when we start dealing with friction, because I'm starting in motion, I know that I'm already in motion, I immediately know that I can go ahead and use kinetic friction. The distance lies a distance of 8 meters, so that would be delta x before coming to a rest. So V final is equal to 0 meters per second. Find the coefficient of kinetic friction between the disk and the deck. So just like any problem, the very first thing I want to do is go ahead and draw my free body diagram. There's a keyword here that where it says it leaves the queue. So we're talking about it after it's already left the queue. So if I'm going in this direction, the only thing I actually have is force of friction, force of kinetic friction going in this direction. I do have force of normal and force gravity. So I'm going to do two sum of force equations. And here we're going to have positive, positive, just for the sake of this. So I would say sum of force in the y direction, I have force normal minus force of gravity equals, well, it's only moving horizontally. So in the y direction, it's still 0. So I can immediately say force normal equals force of gravity. So force normal equals mg. I can use this as I solve. Then I'm going to go into the x direction. The only force I see in the x direction is the force of kinetic friction. Because my box is moving this way, but the acceleration would actually be this way. So you know what I'm going to do? I'm actually going to come over here and I'm going to make positive in this direction so that they go in the same way. The acceleration is in the direction of the force. So I'm just going to say force of kinetic is equal to ma of the x. Because I'm using kinetic, I know that that is mu k force normal. Well, force normal is equal to mg. So I can say force of kinetic is equal to mu k mg, which is equal to m acceleration. Well, here off the bat, this happens a lot. It doesn't happen always, but it happens a lot when we're doing friction problems, which is the mass cancels away. So that's a hint. Oftentimes, a problem won't give you a mass. Sometimes, if they don't give you a key part that you think you might need, it's because it cancels in the solving process. Here, they did give me the mass, but I found out right now I don't actually need it. So I find that mu kg is equal to the acceleration. So therefore, mu k is equal to my acceleration divided by my gravity. Well, I know gravity is 9.81, so all I really need to do is find my acceleration. So I'm going to use kinematics in the information that is given here. I have a v final, I have a v initial, I have a delta x, and I know that I have an equation that relates those. V final squared equals v initial squared plus 2a delta x. So this is 0, 8.5 squared plus 2. I'm going to make my a negative here because they're going in different directions. Remember we said that this is velocity, but my acceleration is in the same direction of my force, so I'm just going to make them opposite. I know I'm not following this, but I am making them opposite. That's what matters. This one is positive, this one is negative because they're going in opposite directions. I can go ahead and solve. That's going to give me 8.5 squared equals 2a delta x. The big thing there was just making sure that these end up being consistent when you move them. Now they're both positive. So we say acceleration is equal to 8.5 squared divided by 2. Delta x, I do know, is 8. When I do this, I get an a equal to, let me pull out my calculator. 8.5 squared divided by 16 gives me 4.52. So I'm going to say my mu k is equal to 4.52 divided by 9.81. So my acceleration and my gravity. And we get a mu k of approximately 0.46. Now some of you guys may be going, hey, but what about our units? We know that we have to put units on things. Mu doesn't actually have units because it's just a coefficient. And here we can actually see that acceleration and gravity is acceleration, so the units cancel. This is the same type of measurement, and so therefore they cancel. Mu does not have units. I don't know why my box just went away. There we go. We'll just circle it. That works. So here's our final answer. So once again, I listed my notes. I did a free body diagram. I did a sum of forces in the y direction, a sum of forces in the x direction. I knew I was solving for mu k, so I said, how far can I get that? I found out that mu k was actually just acceleration over gravity. So I had gravity. I need a mu k. That means I had to have enough information to find acceleration. I used my kinematics to get there. So let's look at the next problem. This is a really cool problem that I like to do in class when we have the time and to actually see how this works. It says you have a hardcover book. It's resting on a tabletop with its front cover facing upward. So that's what we have going on here. We're actually pulling the front cover up some. You place a point on the cover and very slowly open the book until the coin starts to slide. The angle max, known as the angle of repose, is the angle the front cover makes with the horizontal just as the coin starts to slide. Find the coefficient of static friction between the book cover and the coin in terms of theta max. So we have some things going on. First off, we have this incline plane. This is our theta, and we have the coin on it. So that's kind of what our setup is. It's talking about that moment that it starts to slide. When it starts to slide, that means we're talking about our force applied is equal to that force of static max. So whenever we have that, it starts in motion, we're talking about our force applied finally hits that force of static friction maximum. So if I draw a free body diagram for my coin, and yes, I just turned my coin into a box, I like a box. I know that I have a few forces here. My force normal is out this direction. My gravity is directly down. And my force of friction is opposing the movement, so my force of friction is actually up here. As we've done in other incline problems, we're actually going to make our axes, let's actually do this in normal, make our axes parallel and perpendicular to the incline. So this would be my parallel, this would be my perpendicular. That means that the force I need to break down into components is actually force gravity. And so those are my two. If I go ahead and write those out, this is going to be mg sine theta, and this is mg cosine theta. Now I'm ready to write my sum of forces. In the y direction, I have force normal minus mg cosine theta. My movement, if I have any once I start, is in the direction of the incline, so this is set equal to 0. Therefore, I'm going to say force normal is equal to mg cosine theta. This is one of those times, like I said, that force normal is not directly mg. We're on an inclined plane. Force normal is not perfectly equivalent to gravity. It's equivalent to the component in that same direction. I can also do my sum of forces in the x direction. My sum of forces in the x direction, then, or sorry, in the parallel. This should be parallel, and this should be perpendicular. I apologize there. It's hard to get used to. In this direction, I have two different forces. I have mg sine theta minus force of static. we're going to say it's still equal to 0 because it is yet to move. We're at that critical moment where we're going to, as soon as we overcome it by even an ounce, we have now moved on. So here we can say mg sine theta is equal to the Fs max. We're talking about the maximum here. So I do need to make a point that for sake of writing, when I'm writing theta, I'm talking about theta maximum. This is the last theta that we can do without it moving. As soon as my theta is ever so slightly larger than this, the coin will start moving. So we're finding that critical moment right before it starts moving. And we know in the world of calculus, we can find that instantaneous. So even though we aren't using calculus here, it's that same idea. We're finding the actual instant, but we're finding that maximum angle. Because we're dealing with the force of static max, we know that we calculate that as mu s force normal. So we can say that mu s force normal is equal to mg sine theta. Up here, we know that Fn is mg cosine theta. So you say mu s is equal to, or mu s mg cosine theta equals mg sine theta. Once again, this is one of those times I said, notice our mass will cancel out often. Mass cancels, so does gravity. Therefore, mu s cosine theta equals sine theta. Mu s equals sine theta over cosine theta, which I know to be tangent of theta. So our final answer here would actually be that the inverse tan, oh no, we're not even doing, hold on, are we finding mu or are we finding theta? Oh, we're finding mu. So I don't even need to do the inverse. So that is always important to go back and figure out what your question is asking. I would just say mu s is equal to the tangent theta max. And once again, it was extremely important that I make it known that it is theta max because we're saying that exact moment. Otherwise, I could have never used this formula. I would have just said that whatever the force applied was, whatever this theta is, that's just simply my force of static. But we were able to make all of this calculation based on the formula for force static because we're talking about the maximum, and the force static maximum happens at that critical point before it starts moving. So we're talking about that angle. If we go any higher angle, it's going to start moving.